There are places on Earth that silence the noise of time, places where history does not whisper but resonates, where the weight of thousands of years presses into the air itself. The Giza Plateau is one such place. Beneath the eternal blaze of the desert sun, the Great Pyramid stands not as a ruin of the past, but as a question that refuses to fade. Every civilization has left monuments, temples, walls, towers, but none rival the sheer audacity of this single mountain of carved limestone. It was built more than 45 centuries ago, when copper was still new and writing was still young, and yet it rises with a precision that defies belief. More than 2 million blocks of stone, each weighing tons, aligned with such care that even today, the tip of a modern laser meets its corner without deviation. How did they do it? And perhaps more importantly, why? The Great Pyramid is more than an artifact. It is a statement. It tells us that a civilization once existed that understood the earth and the sky as parts of the same equation, that geometry could be a form of prayer, that the weight of stone could be balanced against the movement of stars. Every angle, every chamber, every shaft carved through its heart serves a purpose both practical and symbolic. To study it is to stand at the crossroads of science, faith, and eternity. Modern science has scanned its chambers with cosmic rays, mapped its stones with lasers, and measured its alignments to fractions of a degree. Yet the deeper we look, the more refined the mystery becomes. The pyramid is not a riddle born of superstition, it is a masterpiece of engineering logic. It was conceived not by gods, but by human minds reaching for something greater than themselves. This book is not a tale of alien architects or lost technologies. It is a journey through reality, the proven, the measurable, the awe-inspiring truth of human achievement. We will travel from the desert surface to the chambers below, from the quarries at Wadi al-Jaf to the stars above Giza, tracing the steps of the ancient engineers who transformed limestone into eternity. Because beneath the sands of Egypt, there is more than stone. There is intellect, organization, and vision, the foundation of civilization itself. The pyramid's true secret was never hidden in its passages. It was written into its perfection. And so, we begin our descent beneath the stone, beneath the centuries, to the place where engineering met eternity. The desert stretches endlessly, a golden ocean frozen in silence. At its heart, on the Giza Plateau, a mountain of stone rises from the earth, older than empires and sharper in geometry than any structure made by hand before or since. The Great Pyramid of Giza stands not only as a monument, but as a riddle that has challenged human understanding for more than 4,500 years. Every angle, every block, every alignment carries within it the echo of an intelligence that understood precision long before the age of steel or electricity. When the first rays of the morning sun slide over the horizon, they strike the pyramid's limestone casing with an exactness that seems deliberate, as though the builders measured light itself. Beneath the sand and the weathered edges of time lies an astonishing truth. The structure's base is almost perfectly level. Across more than 5 hectares of foundation, the height difference between the highest and lowest points is less than 2 centimeters. The corners of its square base point almost exactly toward the cardinal directions, deviating from true north by less than 1/15 of a degree. These are not the signs of primitive trial and error. They are the marks of a civilization that mastered both earth and sky. Each of the more than 2,300,000 limestone blocks fits with a precision that modern engineers still admire. Some joints are so fine that a sheet of paper cannot slip between them. The average block weighs about 2.5 tons. Yet others, particularly those within the inner chambers, reach weights of up to 80 tons. The sheer mathematics of moving, aligning, and placing so many stones with such consistency is staggering. Even today, with cranes, lasers, and digital surveying, achieving sub-millimeter accuracy on such a massive scale would require months of planning and measurement. For the ancient Egyptians to have done this with copper tools, ropes, and sledges appears almost beyond comprehension. The Great Pyramid once stood gleaming white beneath the desert Sunday. Its smooth casing stones, polished to a mirror-like sheen, reflected sunlight so brilliantly that the pyramid might have appeared as a beacon visible for miles across the Nile Valley. These casing stones were later stripped away by centuries of quarrying, yet enough remained to reveal the craftsmanship behind them. Each was carved to exact angles, their surfaces ground to fit neighboring stones seamlessly. To cut and polish limestone blocks in such a way demanded not only skill, but an understanding of geometry that rivaled the work of later Greek mathematicians. As we measure the structure today with lasers and satellites, we find no randomness in its design. The sides of the base form near-perfect equilateral triangles, each sloping inward at a precise angle that allowed the pyramid to reach its original height of more than 146 meters. Its proportions follow mathematical relationships consistent with ratios seen in natural harmonies. Some scholars note approximations close to the golden ratio, though this remains debated. Whether by coincidence or design, the geometry of the pyramid reflects a pursuit of perfection that feels both mathematical and spiritual. Archaeologists, engineers, and physicists have studied this monument from nearly every perspective: mechanical, geological, astronomical. Yet one question continues to rise like heat from the desert floor. How? How did a civilization with no steel tools, no wheel-driven cranes, and no written blueprints manage to construct one of the most precise structures on Earth? The answers lie not in myth, but in evidence. Stone quarries have been found along the Nile, and ancient papyri such as the Diary of the Official Mira describe how workers ferried limestone from Tura to Giza. These records show not slaves but organized teams of laborers, each responsible for specific tasks. They were paid in food and respected as specialists. Yet even with this human organization, the logistical challenge remains immense. To build the Great Pyramid within an estimated 20-year period would have required placing roughly 12 blocks every hour, day and night for decades. The foundation upon which this massive structure rests is itself a masterpiece. Before the first stone was set, the builders leveled the bedrock platform with astonishing accuracy. Archaeological evidence suggests that channels filled with water were used as primitive yet effective leveling tools. By carving shallow trenches and filling them, the builders could detect minute differences in elevation, an ancient application of hydrostatics that predated Archimedes by centuries. Once the base was leveled, the first course of limestone was laid down as the foundation upon which all else depended. Every block thereafter was placed in relation to the others, forming a structure so stable that it has survived earthquakes, erosion, and human interference for nearly 5 millennia. The orientation of the pyramid remains true despite centuries of shifting sands and the settling of the plateau. Its precision continues to defy decay, as if the structure was built not merely to endure but to resist the passage of time itself. When we stand at its base and gaze upward, the perspective is overwhelming. The pyramid seems to stretch infinitely, its summit merging with the sky. It embodies the concept of eternity, solid, silent, immovable. Yet behind its stillness lies motion, planning, and relentless labor. It is not the product of magic but of human genius, guided by mathematics and purpose. Modern engineers examining the pyramid have compared its accuracy to the tolerance levels used in high-end construction today. The average error in its sides and angles is smaller than what most skyscrapers achieve, even with computer-aided design. This precision was achieved using simple tools: plumb bobs, sighting rods, leveling instruments made of string, and measuring rods carved from wood. By applying geometric principles and relentless verification, the builders achieved what some have called the first great act of impossible engineering. The magnitude of their accomplishment becomes clearer when one considers the era. The Great Pyramid was completed around 2560 before the Common Era, during the reign of Pharaoh Khufu. At that time, bronze metallurgy had not yet reached Egypt. The wheel was not used for heavy construction, and iron would not appear for more than a millennium. Yet despite these limitations, they achieved architectural perfection on a scale that would not be matched until the modern age. Archaeologists have found remnants of copper chisels, dolerite pounding stones, and wooden sledges used in construction. But tools alone cannot explain the precision seen in the pyramid's core masonry. The alignment of courses, the symmetry of passageways, and the geometry of internal chambers reflect a level of surveying knowledge equal to that used in modern civil engineering. They likely employed rope stretchers specialists who used knotted cords to measure and square angles based on right triangles. This ancient method corresponds to the geometric principles later formalized by Pythagoras. Each block, each corner, and each alignment tells us something about their mindset. Nothing was left to chance. The structure was designed not merely as a tomb, but as a statement of permanence. To them, precision was not decoration, it was sacred. The alignment with the heavens and the stability of the earth were intertwined, reflecting their belief that cosmic order, or ma'at, must be preserved even in death. The pyramid was both an equation and a prayer, written in stone. As the centuries passed, explorers and scholars tried to decode the mystery of its creation. Early travelers from Greece and Rome speculated about hidden machines or divine intervention. Later, in the 19th and 20th centuries, the study of Egyptology brought a scientific perspective. Engineers calculated load distributions, archaeologists mapped construction ramps, and physicists studied alignment patterns. Every layer of evidence peeled back a little more of the enigma, revealing a civilization whose sophistication continues to challenge our modern assumptions. Yet, even now, with all our instruments and data, we still feel a quiet disbelief when we stand before it. The air seems heavier near its base, as though history itself compresses the atmosphere. The stone beneath one's hand carries both the warmth of the sun and the cold of geological time. It humbles us not because it is mysterious, but because it is human. It reminds us that long before engines and steel, the human mind could move mountains with will and mathematics alone. The Great Pyramid of Giza remains, in every sense, a triumph over limitation. It stands not as a puzzle to be solved, but as proof that even in an age of copper and stone, human ingenuity reached for eternity and touched it. And so, the question still echoes across time. How was this possible 4,500 years ago? To answer, we must start beneath the desert where it all began. Beneath the sands of Giza lies a foundation as extraordinary as the monument that stands upon it. When the first explorers descended into the substructures of the Great Pyramid, they found more than chambers and tunnels. They found evidence of a mind that understood both geology and engineering. The pyramid was not placed randomly upon the plateau. It was anchored into the living rock of the earth, as though the builders sought to bind heaven to stone. The bedrock beneath Giza is a massive plateau of limestone, formed millions of years ago when the region lay beneath an ancient sea. Over time, the movements of water carved subtle gradients and fissures through it, creating a natural foundation strong enough to bear the weight of eternity. Geologists studying the site in the 20th and 21st centuries discovered that the builders used this natural platform with surgical precision. Instead of clearing it away, they carved directly into it, shaping the bedrock itself into the first course of the pyramid. This meant that the structure did not sit on soil or sand that could shift, but on solid earth that would not move even under immense pressure. To achieve such an alignment without modern surveying instruments required methods that still inspire astonishment. Recent studies have revealed small trenches around the pyramid's perimeter, ancient leveling systems based on water. The builders filled these channels and observed how the surface of the water naturally sought level. By marking its height along the trench walls, they could compare points across vast distances and ensure that every corner of the foundation rested on the same horizontal plane. This was not merely clever improvisation, it was a deliberate application of hydrostatic principles long before the science of fluid mechanics existed. The result is a foundation so flat that modern engineers have measured deviations of less than 2 centimeters across more than 5 hectares. Once the plateau was leveled, drainage became the next concern. The Egyptians understood the threat of water beneath stone. Seasonal flooding of the Nile could raise groundwater levels unpredictably, and a structure of such mass could not tolerate even minor shifts. Archaeological surveys have found channels and depressions designed to direct water away from the base, suggesting that the builders planned not only for stability, but for longevity. They were not simply stacking stones, they were constructing a geological interface between monument and planet. At the corners of the foundation, socket-like cuts were found in the bedrock, possibly used to anchor large posts or alignment markers. Some scholars propose that these served as fixed reference points for the teams of rope stretchers who measured distances and angles using knotted cords. These cords, stretched taut between posts and cross-checked repeatedly, created a grid that ensured the pyramid's symmetry remained perfect throughout construction. What is remarkable is that such a simple system could yield accuracy on the order of millimeters, a feat that suggests tireless repetition and collective precision. The surface of the foundation also reveals another detail, often overlooked: tiny, regular tool marks etched into the limestone. Under magnification, these marks indicate controlled chiseling using copper tools and abrasive sand. The consistency of the marks shows that hundreds of workers followed standardized methods, likely directed by overseers using predetermined templates. The Egyptians had not yet formalized geometry as a mathematical language, but their practice of measurement was empirical and exacting. They understood that consistency achieved through repetition could yield precision indistinguishable from calculation. In modern construction, engineers rely on blueprints, computer models, and digital simulations. The ancient Egyptians relied on line of sight, water, and intuition refined through generations of craftsmanship. Yet their results rival our own. To measure the pyramid's orientation, researchers have used laser theodolites and satellite imaging. The north-south alignment deviates from true north by an error smaller than 4 arc minutes, less than the width of a human fingernail at arm's length. Achieving that required not only accurate instruments, but a deep understanding of how to reconcile terrestrial and celestial references. It meant knowing how the stars moved, how the sun's shadow shifted, and how to translate that motion into fixed points on the ground. But before alignment came anchoring, the pyramid's blocks rest on the foundation with a kind of interlocking logic. The first course of limestone blocks, some weighing more than 10 tons, was fitted directly onto the carved bedrock. These stones were not cut to identical dimensions. Instead, each was shaped to fit precisely with its neighbors, forming an irregular yet perfectly stable mosaic. This technique distributed weight evenly and prevented shear stress from cracking the base. Over the centuries, earthquakes and erosion have shaken Egypt, but the Great Pyramid remains unbroken. Its endurance is not a miracle, it is engineering born from observation. At certain points beneath the pyramid, tunnels lead downward into the plateau. One such passage, known as the descending corridor, plunges into the bedrock at an angle so exact that its alignment with true north remains consistent over a distance of more than 100 meters. The tunnel leads to a subterranean chamber whose walls appear unfinished, as though abandoned mid-construction. Archaeologists believe this was an early design stage, later replaced by the higher chambers within the pyramid. Yet even here, in the rough surfaces of the rock, the precision of the excavation is unmistakable. The tunnel's straightness suggests continuous measurement during cutting, perhaps using sight lines illuminated by torches reflected in polished copper mirrors. Recent ground-penetrating radar surveys have expanded our understanding of what lies below the plateau. Networks of cavities and shafts extend far beyond the pyramid itself, connecting to natural fissures in the limestone. Some of these were later adapted into tombs, storage chambers, or drainage systems. Others remain inaccessible, sealed for thousands of years. Geological analysis indicates that the ancient builders deliberately exploited these features, using them both as structural anchors and as symbolic thresholds between the world of the living and the underworld. When modern engineers reconstruct the process of leveling and anchoring, they often note the combination of practicality and symbolism. The pyramid was more than architecture, it was a statement about permanence. To secure it to the bedrock was to ensure that the pharaoh's soul, believed to ascend through the heavens, would have an eternal foundation on earth. Every trench, socket, and drainage channel served both engineering and ritual purpose. In the Egyptian worldview, the physical and spiritual were never separate. Stability in stone mirrored stability in the cosmos. Excavations around the plateau revealed that such precision was not unique to Khufu's pyramid. The nearby pyramids of Khafre and Menkaure display similar foundation engineering, suggesting a long tradition of experimentation and refinement. Each successive project improved upon the last, learning from the weaknesses of earlier structures. By the time the Great Pyramid rose, the art of foundation design had reached its zenith. To the modern eye, the desert seems barren, but to the builders, it was a living landscape. The limestone plateau, the Nile's flow, the orientation of the stars, these were all parts of a single system. They did not impose their monument upon the earth, they harmonized it with the terrain. When viewed from above, the pyramids align not only with the cardinal points, but with geological ridges that stabilize the plateau. The choice of location was the first act of genius in a sequence that would culminate in one of the greatest feats of construction ever achieved. Every measurement, every layer, and every stone followed a pattern of purpose. From the bedrock up, the pyramid's creators built not just a tomb, but a physical model of stability itself. Beneath the sands, the foundations of eternity were laid. And from those foundations, the builders would rise, layer by layer, to create a structure whose heart held secrets no one had yet imagined. Deep within the body of the Great Pyramid, the passageways twist and narrow, then rise suddenly into immense chambers of stone and silence. For centuries, explorers believed these interior spaces were simple tomb chambers, built to hold the pharaoh and his treasures. Yet as we learn to look deeper, to measure and scan, rather than simply excavate, it became clear that these spaces served more than ceremonial purpose. They are a marvel of architectural balance, a symphony of mass and void arranged to keep a mountain of stone in perfect equilibrium. The internal architecture of the Great Pyramid is unlike any other structure from the ancient world. It begins with the descending passage that cuts through solid bedrock, the oldest section of the pyramid. Its precision is astonishing. It maintains an almost constant slope over more than 100 meters, with walls that barely deviate from a straight line. From there, a small upward corridor branches off the ascending passage leading toward the heart of the monument. Above it lies a network of chambers and corridors designed with mathematical clarity. The most famous of these is the Grand Gallery, a vast, steeply sloping hall with walls that rise in corbelled layers, each slightly overlapping the one below, forming a narrowing vault that seems to pull the eye upward. The Grand Gallery stretches for more than 40 meters in length and nearly 9 meters in height. Its sides are polished smooth, its joints so precise that modern engineers have compared them to the tolerances of machined metal. This gallery leads to the King's Chamber, the sanctum at the pyramid's core. Constructed entirely from granite blocks transported from Aswan over 800 kilometers to the south, it represents a leap in material and engineering difficulty. Each granite block weighs between 25 and 80 tons, yet they are placed with exactness that defies time. Above the King's Chamber are 5 smaller compartments known as relieving chambers. Their purpose is not decorative. They form a structural system designed to distribute the weight of the pyramid so that the chamber below does not collapse under the mass of millions of tons of stone. The granite beams that span these chambers are monumental, some weighing more than 50 tons. Yet they are positioned with precision, angled and layered, so that each transfers pressure outward rather than downward. This design shows a profound understanding of force and stress, concepts that would not be formalized until thousands of years later, when modern archaeologists and engineers began to study these inner spaces with advanced tools. They discovered that the precision was not limited to the visible chambers. Using muon radiography, a technology that detects cosmic particles passing through stone, scientists from the Scan Pyramids project revealed new voids hidden deep within the pyramid structure. These findings, published in the 21st century, confirmed that unknown cavities exist above the Grand Gallery and elsewhere, some as large as a passenger jet fuselage. The discovery reignited debate about the internal design. Were these voids intentional, part of a stress relief system? Or were they symbolic, representing pathways for the pharaoh's soul to ascend to the heavens? The physics behind muon detection is itself a marvel of modern ingenuity. Muons are high-energy particles that constantly rain upon Earth from cosmic rays. When they pass through solid materials like stone, their paths bend or slow depending on density. By measuring how many muons reach detectors placed inside the pyramid, scientists can infer the existence of empty spaces. The results revealed patterns too deliberate to be random, confirming that the ancient builders had engineered voids with precise geometry long before the age of physics. Inside the pyramid, the acoustic properties are equally striking. Experiments with sound mapping have shown that the dimensions of the king's chamber produce standing waves at specific frequencies. These resonances are not accidental. They are a product of the room's proportions and the material properties of granite. Some researchers suggest that the Egyptians may have noticed these effects and incorporated them symbolically, associating vibration and sound with divine energy. While such interpretations remain speculative, the measurements themselves are real. The chamber responds to vibration in a way that amplifies low frequencies, as though the stone itself remembers the human voice. The precision extends beyond geometry and sound. The temperature inside the pyramid remains remarkably stable, hovering around 20 degrees Celsius year-round, regardless of the heat outside. This natural climate control is due to the sheer mass of stone, which absorbs and releases heat slowly. Yet even this could have been anticipated. The ancient builders seem to understand the behavior of materials not just statically, but dynamically, designing a structure that interacts with the environment in equilibrium. Archaeological teams have mapped every accessible passage and cavity, yet large portions of the internal architecture remain sealed. The blocked ascending corridors and mysterious door-like slabs discovered by robotic probes suggest there are more chambers yet to be found. In one exploration, a small robotic camera sent into a narrow shaft discovered copper fittings embedded in stone doors, a detail so refined that it hinted at both mechanical and symbolic design. Were these doors meant to seal hidden chambers or to represent thresholds between worlds? In Egyptian theology, both explanations may be true. To the ancient mind, the pyramid was more than a tomb. It was a cosmic machine. Its geometry, orientation, and internal layout mirrored the journey of the soul. The ascending and descending passages represented the duality of life and death, the movement between the earthly realm and the celestial. The Grand Gallery's soaring form may have symbolized the passage of ascension, while the king's chamber represented rebirth into eternity. Every corridor and cavity, every angle and resonance, was part of a greater equation of faith and physics. Even the placement of the sarcophagus in the king's chamber suggests deliberate calculation. It is carved from a single block of red granite, its dimensions perfectly matched to the chamber's interior. When modern surveyors measured it, they found that it had been hollowed with precision that implies the use of advanced abrasives, possibly copper saws tipped with quartz sand. The corners are true, the surface is polished. It was not built inside the chamber, it was placed there before the chamber was sealed, meaning the chamber itself was constructed around it. The relieving chambers above, once thought to be empty voids, contain ancient graffiti red ochre marks left by the workers themselves. These markings, identifying crews with names like the Friends of Khufu, prove beyond doubt that the pyramid was built by human hands, not by myth or mystery. They are signatures of pride from a civilization that built with purpose and mastery. As we continue to explore the pyramid's depths, the picture that emerges is not of lost technology, but of extraordinary human intelligence. Every discovery, from the hidden cavities revealed by muons to the leveling of bedrock beneath, adds another layer of evidence that the builders of Giza combined empirical observation with spiritual conviction. They measured the world through both science and faith, uniting them in stone. And yet, for all we know, much remains hidden. The pyramid still guards secrets within its massive heart, chambers that have not felt light for 45 centuries. They may contain nothing but air and silence, or they may hold inscriptions, objects, or insights that will reshape what we know about the ancient world. What is certain is that each revelation deepens rather than diminishes our sense of wonder. To build such a structure, the Egyptians needed more than stone and manpower. They needed control over forces gravitational, structural, and human that no civilization had ever mastered before. Their next challenge was not to place stones upon the ground, but to lift them toward the sky, raising millions of tons of limestone and granite into an ordered mountain. For that, they would have to move the unmovable. The desert remembers. Beneath the shifting sands of Giza lies a world older than the pyramids themselves, a foundation not of myth but of stone and precision. Before a single limestone block was raised toward the sky, the builders turned their eyes downward, into the bedrock that would bear the weight of eternity. The Great Pyramid could not have endured 4,500 years without what lies unseen, its perfectly leveled base, its anchored geometry, and its union with the living rock of the earth. Long before modern surveying or mechanical drills, ancient engineers faced the first and most essential challenge: where to build. The Giza Plateau was not chosen for beauty or chance. It was chosen because it was strong. Beneath a thin layer of sand and weathered crust lies a vast formation of Eocene limestone, laid down by an ancient sea millions of years earlier. The rock is dense, stable, and layered like a natural scaffold. The Egyptians, through generations of observation, learned that this bedrock resisted erosion and vibration. When struck, it sounded solid and unbroken, a tone that told them it would hold. The builders began not by adding stone, but by carving into it. Archaeological surveys show that they cut away irregularities, filling natural fissures with limestone chips and gypsum mortar to create a surface as level as still water. Even today, with satellite measurement and laser scanning, the base of the Great Pyramid remains almost perfectly horizontal. Across an area of more than 5 hectares, the difference in height between the highest and lowest corner is less than 2 centimeters. That degree of precision over such a distance would challenge even a modern construction crew. To achieve it in an age of copper and rope required a mastery of measurement few civilizations would rediscover for millennia. Evidence suggests they used one of the simplest yet most brilliant tools ever conceived: water. Shallow trenches cut around the foundation were filled until the surface settled into a perfect plane. By marking the height of the water along the trench walls, workers could read where the ground rose or dipped, shaving away high points until the entire expanse lay flat. It was an early application of hydrostatics, a science that would not be formally understood until the time of Archimedes thousands of years later. Yet the Egyptians had already applied it on a monumental scale. Drainage was another hidden triumph. The plateau was not immune to rain or the seasonal swelling of the Nile. Without control, water could seep beneath the stones, causing the foundation to shift or crack. To prevent this, the builders carved channels and slopes into the bedrock, guiding runoff away from the core of the structure. These systems remain visible in places, etched like veins in the limestone. They transformed the pyramid's base into a kind of geological machine, self-stabilizing, self-preserving, eternally balanced. At each of the 4 corners of the Great Pyramid, ancient socket cuttings can still be seen in the rock. These are not decorative. They may have held posts used as alignment markers or anchor points for measuring ropes. Teams of rope stretchers, specialized surveyors known from ancient inscriptions, would have fixed their cords between these posts to square the corners and establish the grid on which the pyramid was built. The cords were knotted at precise intervals, allowing distances and right angles to be measured with remarkable consistency. This method predated formal trigonometry but achieved the same purpose. By overlapping chords and verifying diagonals, they could test for true right angles, ensuring the base remained geometrically perfect. This precision extended to the cutting of the first course of stones. These foundational blocks were enormous, some weighing more than 15 tons, and they were placed directly onto the leveled bedrock. Each was carved to fit the next like pieces of a giant puzzle, interlocking irregularly but fitting so tightly that no mortar was needed. This irregular interlock spread the weight evenly, reducing stress and preventing the blocks from slipping even if minor settling occurred. It was the ancient equivalent of seismic engineering. The more one studies this hidden layer, the clearer it becomes that the Egyptians built from the ground up with a philosophy of permanence. The foundation was not meant to be seen, yet it received the same precision as the visible outer casing. In modern architecture, the invisible parts of a structure often receive less attention, yet here the reverse is true. The unseen was sacred. To them, the stability of what lay beneath determined the fate of what would rise above. Recent geological surveys using electrical resistivity and seismic imaging have confirmed that the limestone beneath Giza remains astonishingly intact. The weight of the pyramid, pressing down for more than 4,000 years, has not fractured the plateau. Instead, it has compacted it further, sealing microfissures under pressure. Nature and engineering combined to form a single, stable whole. Even earthquakes that have damaged temples and obelisks across Egypt have left the pyramids largely unshaken. Their strength lies in the bond between bedrock and block, a dialogue between nature and design. Modern engineers studying the site have remarked that such a foundation could not have been achieved without detailed planning. It implies surveying instruments, sighting lines, and measuring tools of extraordinary refinement. Wooden leveling rods and copper plumb bobs would have been used to verify alignment. Simple as they sound, these tools, when applied systematically, could yield results within millimeters. The builders did not need machinery, they needed method. The level of coordination required suggests a vast organization of laborers, architects, and geologists, long before the first stone was set. The quarrymen cutting the limestone needed to know the exact size of the blocks, the masons shaping them needed to understand the curvature of each side, and the foundation teams had to align everything with celestial north. It was a dance of precision between thousands of hands guided by a single mathematical vision. Standing today at the pyramid's edge, most visitors never see this foundation. The sand hides it, the centuries have buried it, yet it is the quiet miracle that made everything possible. The Great Pyramid is a monument to what we can see, but it is held up by what we cannot. Beneath the desert, the first engineers of history turned rock into balance, and balance into eternity. The Egyptians were not simply builders, they were students of the earth. They read the land like astronomers read the sky, recognizing that stability comes from harmony. To them, a structure that ignored the ground beneath it could not last. The pyramid's perfection was not imposed on nature, but drawn from it, carved from its strengths, adapted to its flaws. This philosophy of building with the earth rather than against it was their first great act of genius. From this foundation rose the pyramid itself, each layer resting upon a precision that remains invisible yet indispensable. Every centimeter of stone above was measured, planned, and placed in relation to the base below. From the bedrock up, every layer was designed with purpose. And now, as we rise from the depths of limestone and begin to explore what the ancient builders raised above it, the mystery deepens not downward, but upward into the chambers that held the heart of the pharaoh and the secrets of ancient engineering. Beneath the sun that scorches the Giza plateau, the builders of ancient Egypt began their ascent. From the level bedrock they had carved so precisely, they raised the first layer of stone, each block resting upon the foundation with deliberate care. What began as geometry carved into the earth now rose toward the heavens as a vast, ordered mountain. Every tier of limestone, every edge aligned to the next, revealed that their understanding of structure was not crude or instinctive, but mathematical and systematic. They were not guessing their way upward. They were following a plan drawn from the logic of balance, the laws of physics, and the rhythm of the stars. Each layer of the Great Pyramid was a stage of coordination unlike anything attempted before. The blocks of limestone were quarried from the plateau itself for the lower courses, while finer white limestone from Tura was reserved for the outer casing. The quarries near Giza still show tool marks from copper chisels and pounding stones of dolerite, a volcanic rock hard enough to shape limestone through relentless impact. The workers carved channels around each block until it could be freed from the bedrock, then levered it onto sledges made of wood. Thousands of such stones were moved in this way, their journey measured not in kilometers but in precision. The true mystery of construction was not in cutting the stones but in moving them. Dragging multi-ton blocks across rough sand would have been nearly impossible if the sand behaved as it does underfoot today, loose, shifting, and heavy with friction. But ancient builders understood the desert in ways few modern observers appreciate. In 21st century experiments, physicists from the University of Amsterdam confirmed that when sand is slightly moistened, its grains form weak bonds that reduce friction dramatically. Under these conditions, the force needed to pull a sledge is reduced by half. Depictions on ancient tomb walls show precisely this method, workers pouring water before the moving stone. It was not ritual, as once thought, it was science in action. As the first layer of the pyramid rose, ramps of compacted limestone chips and clay were likely built around the edges. These served as both pathways and supports, allowing sledges to climb gradually as the monument grew. The exact configuration of these ramps remains one of archaeology's most enduring debates. Some propose long, straight ramps, stretching for hundreds of meters, while others, such as French architect Jean-Pierre Houdin, argue for an internal spiral ramp built within the pyramid's outer shell. Yet, regardless of form, all evidence points to the same principle. The Egyptians used geometry, not guesswork. The slope of the ramp, the gradient of friction, and the rate of ascent were all controlled through measurement and repetition. Excavations at the quarry of Hatnub in Middle Egypt uncovered the remnants of a ramp system that may hold the key to this enigma. There, researchers found two parallel staircases flanking a central ramp with post holes that once anchored wooden poles. These poles, when fitted with ropes, could have been used as a pulley-like system to lift and drag heavy blocks upward with fewer men. The discovery, dated to roughly the same era as Khufu's reign, shows that such lifting technology was not beyond Egyptian engineering. It was simple, efficient, and scalable, a human-powered machine of stone, rope, and will. The movement of the blocks from quarry to pyramid was not chaotic labor, but an orchestration of timing and teamwork. Archaeologists at Giza have uncovered the remains of worker villages, bakeries, breweries, and medical stations. These were not slave camps, but organized communities. The workers were skilled, fed, and housed, forming rotating crews that worked in coordinated shifts. Their graffiti, still visible in hidden chambers, shows pride in their work. Teams bore names like the Drunkards of Menkaure or the Friends of Khufu. This was not forced labor, it was national purpose. The building of the pyramid was a unifying act that tied faith to engineering, devotion to design. Every layer rose according to plan. The Egyptians measured elevation not by abstract mathematics, but by using physical instruments. They may have used plumb lines and leveling cords, checked with sighting rods aligned to the horizon. Each new course of stone was laid back slightly from the one below, forming the slope that would give the pyramid its perfect shape. Over the decades of construction, the builders maintained this slope with astonishing precision, ensuring that all four sides met at the apex without cumulative error. In modern terms, this required an understanding of error propagation, the awareness that even small deviations at the base would magnify dramatically at the top. When the pyramid reached the height of a modern 15-story building, the challenge became not just moving stone, but positioning it accurately at increasing altitude. Teams likely built and dismantled ramps repeatedly, recycling material as they climbed. Others prepared the next set of blocks below, ensuring that the flow of materials never stopped. To complete a monument of this scale in roughly 20 years required relentless coordination. Based on modern calculations, roughly 12 blocks per hour had to be placed around the clock. This was a continuous industrial operation thousands of years before the concept of industry existed. Even the surface of each block was shaped with intent. The rough faces inside the core were left unpolished, but the outer casing stones were cut with precision so fine that when placed together, they formed invisible joints. These outer stones were arranged so that the edges of each course locked into those above and below, distributing pressure and stabilizing the structure. When sunlight struck the finished surface, it reflected brilliantly, turning the pyramid into a radiant beacon visible across the valley. Travelers from distant lands described it as if it were made of pure light. Modern engineers who have reconstructed the process using ancient tools report that such precision is achievable with patience, teamwork, and knowledge of leverage. Simple wooden levers, used systematically, can move and position stones of enormous weight. By inserting small wedges, lifting slightly, and sliding blocks incrementally, ancient workers could achieve sub-millimeter adjustments. When multiplied by thousands of workers over decades, this precision becomes monumental. The pyramid is not evidence of lost technology, it is evidence of perfected technique. By the time the Great Pyramid reached its final height, the ramps were removed, leaving only smooth faces that once gleamed in the sunday. At the summit, the builders placed a capstone, possibly gilded or covered in electrum, to catch the first light of dawn. From base to apex, the structure formed a geometric ladder connecting earth and sky, bedrock and starlight. The stones were no longer inert matter, they had become a map of the cosmos in solid form. The pyramid's construction was an act of faith expressed through engineering. Every movement, every lift, every alignment was both practical and sacred. To them, lifting stone was lifting spirit. They believed that the act of creation mirrored that of the gods, who raised the first mound of land from the primeval waters. Each block was a reenactment of that cosmic birth. It is easy, from the distance of millennia, to mistake devotion for superstition. But in the careful design of ramps, levers, and sledges, in the rhythm of measured labor, we see reason, not ritual. The builders of Giza united physics with purpose. They used their knowledge of balance, friction, and human strength to achieve what seemed impossible, not through magic but through method. And yet, even this astonishing feat, the movement of millions of stones, was only half the challenge. The question that has haunted archaeologists and engineers alike remains: how did they lift them, raising tens of thousands of tons layer upon layer until they reached the heavens themselves? The answer lies in the next step of their genius, the mastery of elevation, the secret of the Great Lift. The ancient builders of Egypt faced a challenge unlike any before them: to lift stone upon stone, to raise the pyramid from the earth toward the heavens. They had to master forces greater than their own. Every layer of the structure weighed thousands of tons. Each tier grew narrower, steeper, more perilous. The higher they built, the more difficult the ascent became. Yet they did not stop. They calculated, adjusted, and engineered a method to move the immovable. The mystery of how they lifted these immense stones has haunted scholars for generations. Countless theories have been proposed: straight ramps stretching for hundreds of meters, spiral ramps winding around the pyramid's outer face, or even ramps concealed within the body of the structure itself. What unites all these ideas is not contradiction but admiration for whatever method they used. The result was one of the most precise and enduring constructions ever achieved. Archaeological evidence gives us glimpses of their strategy. The quarries near the plateau show cut marks, angled in ways that suggest stones were extracted and pulled along ascending paths rather than lifted vertically. These paths may have been integrated ramps, built gradually as the pyramid rose. At the unfinished pyramid at Zoyet El Aryan, remnants of large inclined planes of limestone chips have been found, ramps whose slope and width match the logistics of block hauling. They were steep, but not impossibly so, angled to balance speed and safety. A straight ramp too long would have required more material than the pyramid itself. A spiral ramp too tight would have obstructed alignment. Somewhere between these extremes lay the true method, a practical compromise perfected through experience. Jean-Pierre Houdin, a modern architect, proposed that an internal spiral ramp wound upward inside the pyramid's outer shell, hidden from view. His theory, supported by three-dimensional scans of internal density variations, suggests that as the pyramid rose, workers used internal corridors to haul stones upward in stages, turning corners at platforms and continuing higher, without dismantling external ramps. This method would have protected the fragile casing stones and allowed alignment to be checked constantly. While not proven, it fits the available evidence and solves multiple engineering puzzles at once. But even without internal ramps, the Egyptians demonstrated an extraordinary grasp of leverage and counterweight mechanics. Scenes in tombs and inscriptions show workers using wooden levers, stone fulcrums, and ropes to tilt and guide blocks into position. By inserting small wedges and alternating pressure, they could raise heavy blocks incrementally, shifting them a few centimeters at a time. It was slow but relentless, a rhythm of lift and rest repeated across decades. With enough teams working simultaneously on each side, progress was continuous. Physics reveals the brilliance behind their approach. A stone of 2.5 tons on a ramp inclined at 10 degrees exerts a downward force that can be countered by fewer than 50 men using coordinated pull and leverage. On a ramp softened with water to reduce friction, even fewer would suffice. Multiply this by hundreds of crews operating day and night, and the impossible becomes merely methodical. Their achievement lay not in discovering new laws of physics, but in applying those laws to perfection with the means they had. Recent studies of unfinished monuments, such as the Pyramid of Djedefre at Abu Rawash, reveal ramp fragments with lateral walls, evidence of retaining structures built to stabilize the incline as height increased. These suggest that the Egyptians adjusted their ramps dynamically, recycling materials as they climbed. Once a section reached its final level, the ramp would be dismantled, its stones reused higher up. Nothing was wasted. The process was circular and efficient, a continuous transformation of matter into monument. When the pyramid neared completion, the precision of alignment demanded an almost obsessive attention to geometry. The topmost blocks, the so-called pyramidion stones, had to meet at a single point above the exact center of the base, a convergence of 4 planes aligned to true north, south, east, and west. Even the slightest cumulative error could have skewed the summit, yet measurements show deviations of only a few centimeters. This feat could only be achieved if every layer below was checked, measured, and corrected before the next began. The builders must have employed sighting poles, cords, and small viewing frames to verify angles against the horizon. Each correction was a conversation between man and monument, between intention and gravity. The final lifting stage, placing the massive granite beams of the king's chamber and the relieving chambers above it, remains one of the greatest accomplishments in ancient construction. These stones, some weighing more than 50 tons, were hauled from Aswan over 800 kilometers away. To move them upward within the structure required planning at an architectural level. The builders likely left open ramps and spaces within the pyramid's growing body, hauling the beams through internal channels before sealing them forever inside. The positioning of these blocks was so perfect that the chambers they support have not shifted even a millimeter in 4.5 millennia. Each block, each lift, each alignment tells the same story. The Egyptians were not improvising. They were executing a master plan refined over generations. The earlier pyramids at Medum and Dashur reveal their learning process. The collapsed forms of early attempts stand as evidence of failure studied and overcome. By the time of Khufu, the art had matured into science. They had discovered how to read the load-bearing capacity of limestone, how to distribute weight through corbelling, and how to build not by guess but by principle. When we look at the Great Pyramid today, we see the outcome of that evolution, a structure that is both massive and graceful, imposing yet mathematically elegant. To raise it was to raise human understanding itself, to show that through discipline and design, even stone could be persuaded to defy its own weight. The ramps were long ago dismantled, the scaffolds vanished into dust, but the monument endures. What remains is not the process, but its perfection. The builders left no written blueprints, no diagrams, only the silent geometry of what they achieved. In that geometry lies the proof of their genius. The mastery of lifting and alignment was not the end of their engineering, but the beginning of a greater revelation. For when the last stone was set and the surface gleamed white in the desert sun, another precision revealed itself, one not of mass, but of direction. The Great Pyramid was not only an act of construction, it was an act of orientation. Its sides faced the cardinal points of Earth with such accuracy that even modern compasses struggle to match it. This was not coincidence but calculation, for the builders had aligned their monument with the very axis of the world. Inside the Great Pyramid of Giza lies a world few have ever seen. It is a labyrinth of narrow corridors, ascending passages, and chambers that rise in deliberate sequence from the heart of the bedrock to the very center of the structure. For centuries, these inner spaces were thought to be simple burial rooms or symbolic tunnels, carved to protect the pharaoh's body and guide his soul to the afterlife. But as science advanced and new tools pierced the darkness, a deeper truth began to emerge. The pyramid is not solid, nor is it hollow. It is alive with geometry, pressure, and design. The first explorers who entered its depths carried torches that flickered against the smooth limestone walls. The air was still, heavy, and ancient. They crawled through the descending passage, a tunnel that plunges deep into the bedrock beneath the pyramid. This passage, angled downward with unwavering precision, was carved before the superstructure itself was raised. Its gradient, measured in modern times, is astonishingly consistent, descending at a fixed angle of about 26 degrees, its straightness verified by laser instruments. It ends in a rough-hewn chamber cut directly into the limestone of the plateau. This unfinished room, long believed to be an abandoned burial chamber, marks the first step in the pyramid's architectural evolution. It is the memory of a plan revised, a glimpse into the experimentation that shaped perfection. Halfway down the descending passage lies a junction, a fork where another corridor ascends. This narrow upward tunnel leads into the internal architecture, that makes the Great Pyramid unique among all of Egypt's monuments. The ascending passage rises into the heart of the structure, its walls polished, its angle precise. From it, two great paths diverge, one leading to the so-called Queen's Chamber, the other to the Grand Gallery, which in turn leads to the King's Chamber. This branching system forms the skeleton of the pyramid's interior, a series of connected volumes carefully balanced to manage both symbolic and physical forces. The Queen's Chamber, smaller and set lower within the structure, sits directly on the pyramid's central axis. Its function remains debated. Some argue it was intended as an early burial chamber, later replaced by the King's Chamber above. Others see it as a symbolic heart of the structure, representing the transition between earth and sky. The chamber's walls are smooth and unadorned, but two narrow shafts rise from it at an angle, cutting through meters of stone toward the outer surface. These shafts, long sealed, were rediscovered in the 19th century and later explored with robotic cameras. Their construction is flawless, precisely angled, narrow as a human arm, extending for more than 40 meters through solid limestone. What purpose could such tunnels serve? For years, they were assumed to be air shafts, meant to ventilate the pyramid. Yet, their direction and precision suggest something more profound. When their angles are traced outward, they align with stars that held sacred meaning in Egyptian cosmology. The northern shaft points toward Thuban, once the pole star around 2500 before the Common Era, while the southern shaft aligns roughly with the belt of Orion, the constellation associated with Osiris, god of resurrection. These alignments are too deliberate to be accidental. The shafts were not made for air but for eternity pathways through which the pharaoh's soul might ascend to the heavens. The Grand Gallery, rising above the Queen's Chamber, is perhaps the most awe-inspiring corridor ever built in stone. It stretches for more than 40 meters, its walls corbelled inward in 7 overlapping layers that form a vault high enough for sound to echo endlessly. Every block is perfectly placed, each joint seamless. The floor is lined with a deep central groove flanked by smooth ramps, and along the sides are rectangular slots cut with regular intervals. These may have supported wooden beams or planks, perhaps for scaffolding or for sliding large stones upward toward the King's Chamber. The gallery's geometry is not decorative, it is structural. The corbelled design disperses the enormous weight pressing down from above, preventing collapse. At the gallery's summit lies the antechamber, a narrow passage leading into the King's Chamber, the heart of the pyramid and one of the most precisely built rooms in history. Constructed entirely of red granite from Aswan, the chamber measures 10.5 meters by 5.5 meters, with a height of nearly 6 meters. Every surface is flat, every joint tight. The sarcophagus within, carved from a single block of granite, is slightly too large to have been moved through the passageways. This means the chamber was built around it, sealing it forever inside. Above the King's Chamber are 5 smaller compartments, known as relieving chambers, first discovered in the 19th century by Colonel Howard Vyse. Their function is structural genius. The weight of the pyramid above more than 2 million tons is redistributed across these layers of granite beams, each chamber relieving stress from the one below. The uppermost chamber has a ceiling of granite slabs arranged in a pointed arch, the oldest known use of this technique. Without these chambers, the King's Chamber would have collapsed under its own roof long ago. In recent decades, technology has revealed even more hidden spaces within the pyramid. Using muon tomography, a method that measures cosmic particles passing through stone, the Scan Pyramids project detected previously unknown voids above the Grand Gallery. These cavities, invisible to the naked eye, show patterns too regular to be natural. They may be extensions of the relieving chambers, or perhaps new architectural spaces whose purpose remains unknown. One of them, the so-called Big Void, is large enough to hold an aircraft fuselage. Its discovery, published in the early 21st century, proved that even after 4.5 millennia, the Great Pyramid still holds secrets untouched by human hands. These discoveries reignited debates about the true design intentions of the ancient builders. Were these voids purely structural, relieving stress and stabilizing the pyramid's interior? Or did they serve a symbolic function, balancing visible and invisible worlds within the pharaoh's tomb. To the Egyptians, there was no distinction between the physical and the spiritual. The two were bound together in the concept of Ma'at, cosmic order. The pyramid's inner voids may have represented the celestial spaces through which the pharaoh's soul would travel, mirroring the empty sky above. Acoustic and thermal studies have added yet another layer to the mystery. Infrared scans have detected temperature anomalies along certain sections of the pyramid's face, hinting at internal cavities or passages not yet explored. Within the king's chamber, researchers have measured resonant frequencies amplified by the granite walls. These tones are not random. The dimensions of the chamber naturally produce standing waves that amplify sound, creating vibrations that can be felt through the stone. Some believe the builders may have noticed this resonance and incorporated it intentionally, associating vibration with spiritual transformation. Whether symbolic or accidental, it adds to the sense that the pyramid is not just a structure, but a living instrument of physics and faith. Even the smallest architectural details seem to carry meaning. The shafts from the king's chamber also align with specific stars Kochab in the constellation of Ursa Minor and Alnitak, the easternmost star in Orion's belt. The precision of these alignments implies that the builders observed the sky carefully, perhaps using simple tools such as a Merket and plumb line to fix the stars' positions on the horizon. From this celestial framework, they oriented the entire monument, ensuring that its spiritual and geometric centers were one and the same. When explorers stand within the king's chamber today, the silence is overwhelming. The air feels dense, almost charged. It is as if the mass of stones surrounding the room concentrates time itself. No decoration covers the walls, no inscriptions name the dead. The pyramid's grandeur lies not in its ornament but in its design. It is the ultimate expression of perfection through emptiness, a statement of power written not in words but in geometry. These inner spaces, both seen and unseen, form the heart of the Great Pyramid's enduring mystery. They reveal a civilization that understood not only how to build, but how to balance, how to channel, and how to symbolize the universe in stone. The pyramid is not simply a tomb. It is a three-dimensional equation, one that expresses harmony between gravity, astronomy, and the human spirit. The more we study its chambers, the clearer it becomes that the Egyptians achieved something greater than immortality through architecture. They achieved timelessness through precision. The voids within the pyramid are not absences, they are expressions of control, the deliberate shaping of emptiness to hold eternity itself. The stones of Giza were born from the earth, but they did not remain there. To build a monument that could touch the sky, the ancient engineers had to first conquer distance. Each block, millions in total, had to be quarried, shaped, transported, and raised with a precision that still defies comprehension. How a civilization of copper tools and wooden sledges achieved such flawless logistics is one of the greatest engineering triumphs of all time. Along the banks of the Nile, sunlight gleamed on white limestone cliffs at Tura, and deep in the southern quarries near Aswan, red granite veins ran through the bedrock. These were the materials of eternity. The limestone would form the gleaming outer skin of the pyramid, while the granite would become its heart, used in the king's chamber and internal structures where strength mattered most. The journey from quarry to Giza was as vital as the building itself. The stone had to move hundreds of kilometers, some from upstream and others from nearby sources, each weighing between 2 and 80 tons. The Nile was the secret to this feat. Every year, when the floods swelled its waters, Egypt became a land of floating cities. The river linked quarries, workshops, and the construction site in a living chain of movement. Excavations at Wadi al-Jarf, on the western shore of the Red Sea, revealed the diary of an overseer named Mira, written on fragile papyrus and preserved by the desert. His journal describes the transport of limestone blocks from Tura to the Giza plateau. The details are mundane yet profound entries of men moving stone day after day, using boats, canals, and causeways. This was the first recorded instance of organized industrial logistics in human history. Mira's team sailed their cargo through a network of canals that reached inland toward the construction zone. Archaeologists have uncovered the remains of these ancient waterways, buried under millennia of sand. Channels were dug from the Nile to the base of the plateau, forming a harbor where boats could unload their massive cargoes directly beside the building site. The evidence is unmistakable. Giza was once a port. In the season of inundation, the pyramid was connected to the river, allowing stone to glide effortlessly across water instead of dragging it across desert. Once the blocks reached land, another transformation began: the triumph of human physics over sheer mass. The stones were loaded onto wooden sledges and hauled across prepared paths of sand and crushed limestone. For centuries, scholars imagined teams of slaves struggling under unbearable weight. Modern evidence tells a different story. Reliefs from tombs near the pyramids show organized crews, hundreds strong, pulling in rhythm while a single man pours water on the sand before them. For generations, this image was interpreted as a ceremonial act. Today, we know it was science. In 2014, a team of physicists from the University of Amsterdam demonstrated that slightly wet sand cuts friction almost in half. Water binds grains together, forming a firm but slick surface that prevents sledges from sinking. The Egyptians, through experience, discovered this principle long before modern physics could explain it. By controlling the moisture of the sand, they reduced resistance and doubled their efficiency. The act of pouring water was not ritual, it was innovation. Each hauling crew worked as part of a larger system. Some teams managed the ramps, others prepared new blocks at the quarries, and still others repaired sledges or reinforced the ground. Archaeologists at Giza have found the remains of worker villages, complete with bakeries, breweries, and even medical facilities. The workers were not slaves, they were specialists, craftsmen, and laborers living in organized communities. Their diet was rich in protein, their homes sturdy, their tools well maintained. Inscriptions found near their camps bear the names of teams like the Drunkards of Menkore and the Friends of Khufu. These names carried pride. They were builders of eternity, not captives of it. The workforce rotated seasonally, likely drawn from across the kingdom when the Nile floods halted agriculture. During those months, tens of thousands of men joined the construction effort, each group contributing their skill to a collective endeavor that united the nation. It was as much a spiritual project as a civil one. To build the pyramid was to serve the gods, to ensure that the pharaoh, the living embodiment of divine order, would ascend to the stars. Every block moved was an offering of labor to eternity. To transport granite from Aswan to Giza was an even greater challenge. These blocks, used in the inner chambers, weighed up to 80 tons each. They were loaded onto large boats with reinforced hulls and transported downriver during the high flood. Upon arrival, they were pulled overland along causeways, possibly supported by lubricated tracks of wet clay or wooden rollers. The physics is daunting, yet the evidence is clear. They did it not once or twice, but hundreds of times, with consistency and control. Recent discoveries at Hatnub, an ancient alabaster quarry, provided a crucial clue. There, archaeologists found a ramp carved directly into the quarry wall, flanked by staircases with post holes along both sides. These holes once held wooden poles around which ropes were wound. This design formed a primitive yet effective pulley system. Workers could pull from above and below simultaneously, amplifying their strength through leverage. The Hatnub ramp is a microcosm of pyramid logistics, simple, elegant, and grounded in mechanical principles. As the stones approached the construction site, they were sorted and prepared. Quarry marks, still visible on some blocks, indicate their intended location within the pyramid. This level of organization implies an early system of inventory and quality control. Overseers tracked shipments, directed teams, and coordinated arrivals. Nothing was left to chance. The entire enterprise functioned like an ancient machine, powered not by engines but by precision, rhythm, and faith. When one stands before the Great Pyramid today, it is easy to forget that it was once surrounded by docks, canals, workshops, and bustling activity. The desert was not empty, it was alive with sound, movement, and purpose. Wooden sledges creaked across the sand, ropes strained under weight, and commands echoed across the plateau. The air would have been filled with dust, sweat, and the scent of wet limestone. And yet, within this chaos, there was order, an unbroken chain of process that transformed raw stone into geometry. Every phase of movement, from quarry to ramp to placement, was guided by one principle: control. The Egyptians mastered it through observation and repetition. They learned how sand behaved under load, how stone fractured under pressure, and how men could move mountains through unity. They were not guessing. They were experimenting, testing, and perfecting. Each block raised was data for the next. The genius of their logistics does not lie in hidden machines or lost technologies, but in their understanding of natural law. They observed the world and harnessed it. They used water to float, sand to slide, wood to lift, and muscle to sustain. This was not mystical power. It was the scientific method in its earliest form, a civilization learning through practice how to engineer the impossible. As the final blocks approached the pyramid, the ramps grew steeper and narrower. The work became harder, more dangerous, yet the precision never wavered. The rhythm of movement continued until the structure reached its full height, layer upon layer, each aligned to the heavens. The task of moving millions of tons of stone was complete, but the greatest challenge still awaited them. For even after the stones were brought to the plateau, they had to be raised, lifted upward, course by course, to form the sides of the pyramid with perfect alignment. The Great Pyramid rises from the desert like an equation rendered in stone, simple in appearance, infinite in implication. Its geometry is flawless, its mass incomprehensible. To see it is to stand before a paradox: 2.5 million limestone and granite blocks, each weighing between 2 and 70 tons, stacked with near mathematical perfection, more than 140 meters high. And for centuries, one question has haunted every engineer, archaeologist, and scientist who has gazed upon it: how did they lift it? To understand the scale of this problem, imagine a single block of limestone 2 meters long, 1 meter high, weighing more than a family car. Now imagine moving that block not across smooth ground, but up a slope of rising height, aligning it to within millimeters among thousands of others. Multiply that by millions, and the feat becomes almost beyond comprehension. The Egyptians accomplished this without cranes, without pulleys, without iron tools. Their instruments were wood, copper, rope, and will. Yet somehow, they built a structure so enduring that it has survived longer than any written language still in use today. The mystery of the lift has inspired countless theories. The simplest proposes a straight external ramp, stretching from the quarry floor to the rising pyramid. This would require a slope gentle enough to allow movement, perhaps 10% at most. To reach the final height, such a ramp would have needed to extend more than a kilometer into the desert, built from millions of cubic meters of mud brick and limestone debris. That ramp alone would have rivaled the pyramid in mass, and yet not a trace of such a colossal structure remains. The straight ramp theory, once popular, now seems unlikely, not because it was impossible, but because it was inefficient. The Egyptians were builders, not wasteful dreamers. Another idea, more elegant, suggests a spiral ramp wrapping around the pyramid's exterior. This method would reduce the ramp's volume, but it introduces another challenge: visibility. Builders hauling stones up a spiraling slope would lose sight of the corners and alignment, unable to maintain the pyramid's perfect geometry. Modern simulations show that the precision of the corners could not have been achieved if external ramps obscured the edges. The very perfection of the pyramid argues against such a design. The most compelling theory emerged from the work of architect Jean-Pierre Houdin, who proposed that the Great Pyramid may have been constructed using an internal ramp, a hidden spiral corridor ascending within the structure itself. According to his model, the first third of the pyramid could have been built with an external ramp, after which the builders transitioned inward, hauling stones through a spiraling tunnel that wound upward within the pyramid's body. At each corner, large open notches allowed for rotation and redirection. This method would explain the absence of external ramp remains and the precision of the edges. When Houdin's theory was tested against the pyramid's known dimensions, the geometry fit almost perfectly. Later, thermal imaging revealed temperature anomalies in the pyramid's lower levels that could correspond to internal voids following a spiral pattern. While not yet confirmed, this evidence offers the most coherent explanation, yet discovered one that combines practicality, physics, and archaeological logic. The Great Pyramid, in this view, is not a monument of brute labor, but of strategic design. The lift was not conquered through force, but through foresight. To appreciate what this meant for the workers, we must return to the quarries at Tura and Aswan, where the limestone and granite were cut. Once extracted, the blocks were loaded onto sledges, wooden platforms dragged over the desert. Recent experiments led by physicist Daniel Bonn at the University of Amsterdam demonstrated that when sand is moistened to the right degree, about 5% water by volume, it becomes firm enough to halve friction. Ancient reliefs show workers pouring water ahead of sledges, not for ceremony, but for science. The Egyptians had discovered the precise moisture ratio that transformed desert sand into a low-friction surface. This single insight made the movement of multi-ton blocks not only possible but efficient. At the pyramid site, teams of men would have pulled these sledges up ramps using ropes woven from papyrus or palm fiber. Each rope was capable of bearing hundreds of kilograms, and when used in parallel, they could distribute tension evenly across teams. Coordinated through rhythmic chanting, the workers hauled in unison, their effort timed like the beat of a living machine. The ramp's surface was lubricated with clay, water, or oil to reduce drag. Every rise, every pause, was measured. The Egyptians did not improvise, they calculated. The ramps themselves were masterpieces of engineering. They were not single monolithic structures, but adaptable systems. As the pyramid grew, the ramps were dismantled, rebuilt, and extended, always keeping the work area accessible. Some sections likely employed counterweights, stones descending on one side of the ramp to help lift others on the opposite side. Others may have used wooden levers at critical points to nudge stones into exact position. Marks on surviving stones show that the Egyptians rotated blocks as they placed them, fine-tuning their alignment with remarkable dexterity. One of the most telling pieces of evidence for ramp construction comes not from Giza, but from the quarry site of Hatnub in Middle Egypt. Archaeologists uncovered an ancient ramp carved directly into the bedrock, flanked by stairways with post holes. These holes once held wooden poles around which ropes could be looped to create a pulley-like system. The ramp's slope was steep, much steeper than what would be possible without mechanical assistance. Experiments showed that by wrapping ropes around the posts, small teams could haul massive blocks up inclines previously thought impossible. This discovery offers a tangible glimpse into how the pyramid builders may have manipulated weight and force with surprising sophistication. From the combination of these findings, Hatnub's pulley ramp, Houdin's internal spiral, and Bonn's water experiments, a coherent picture begins to form. The Great Pyramid was built through a layered system of ramps, levers, and physics, each adapted as construction rose. The workers were not guessing. They were applying principles of force distribution and friction management, still taught in modern engineering. The genius of their method was its simplicity. Nothing was wasted. Nothing was left to chance. As the pyramid climbed toward the sky, the logistics became as important as the lifting. Every stone had to arrive at the right place and time. Transport routes from the Nile to Giza were carefully timed with the annual flood, when the water level rose enough for barges to deliver stone directly to the construction site. The pyramid's workforce operated in rotating crews, each responsible for specific sectors. The synchronization required to maintain steady progress across millions of blocks is equivalent to coordinating a modern factory. The Great Pyramid was, in essence, the first large-scale industrial project in human history. Even at the highest levels of construction, where the king's chamber and relieving chambers were formed from granite beams weighing up to 70 tons, the builders managed to position each piece with flawless precision. The granite likely arrived from Aswan, over 800 kilometers away, floated down the Nile, and then lifted using combinations of ramps and lever stages. Experiments conducted in modern times with small teams and wooden tools have confirmed that such feats, while demanding, are physically possible with the right mechanical advantage and planning. The Egyptians did not need lost technologies, they needed coordination, geometry, and endurance. Each stone laid higher than the last was part of a rhythmic ascent, a rising order mirrored in their cosmology. The act of building upward was itself a sacred ritual, symbolizing the pharaoh's journey toward the heavens. Every ramp, every layer, every lift carried both physical and spiritual weight. The builders were not merely constructing a tomb, they were constructing the axis of the world. By the time the final blocks reached the summit, the ramp systems had been dismantled and recycled, leaving no trace of the colossal machinery that once surrounded the structure. What remained was the pure geometry of the pyramid itself, perfect, silent, eternal. The evidence of the lift was erased, as if the builders wished only the finished form to endure. Yet, through the dust of centuries, modern science has pieced together their hidden methods, revealing a truth more astonishing than legend. The Great Pyramid was not built by magic or mystery, but by intelligence applied with patience, precision, and unity of purpose. It stands as proof that when human reason is guided by vision, even the impossible can rise from stone. The Great Lift was not just an engineering challenge, it was a triumph of thought. And as the last stone was set and the final ramp dismantled, the pyramid stood complete, a mountain of logic beneath a sky of stars, awaiting the next revelation. How its perfect geometry came to align not only with the earth but with the heavens themselves. The Great Pyramid of Giza is a monument not only to stone but to precision, a harmony between earth and sky. Its sides face the cardinal directions with an accuracy that borders on impossible. The deviation from true north is less than 1/15 of a degree, a precision modern builders struggle to achieve even with laser instruments. How, 4.5 millennia ago, did the Egyptians align millions of tons of stone to the axis of the world? The answer lies not in the desert, but in the night sky. Long before compasses, the heavens were the only map that never changed. To the ancient Egyptians, the stars were not distant lights, but living symbols of order, each movement reflecting the rhythm of creation. When they built a pyramid, they were not just marking land, they were inscribing a cosmic equation, binding heaven and earth. The builders likely began their alignment at night. Standing on the plateau, they would drive a wooden stake into the ground and tie a rope to it, stretching it taut toward the horizon. Then, using a plumb line and a sighting instrument known as a merket, they observed the rotation of the stars around the north celestial pole. By watching two circumpolar stars pass directly above the stake, one descending, one rising, they could fix the true north-south axis. Modern astronomers believe the stars used for this alignment were Kochab in the constellation of Ursa Minor and Mizar in Ursa Major. Around 2500 before the Common Era, these two stars aligned vertically above the horizon in a way that marked true north with extraordinary accuracy. When the sighting lines were fixed, the builders repeated the process to determine the east-west axis, forming a perfect right angle. Ropes were stretched, measurements were checked, and the foundation was squared according to the stars. This union of geometry and astronomy formed the skeleton upon which the pyramid was built. Every block placed thereafter followed the path of that celestial design. To the Egyptians, this alignment was not just technical, it was sacred. The pharaoh, they believed, became one with the gods upon death, his soul ascending to join the imperishable stars that never set. The pyramid's alignment to true north was a literal connection to eternity, a pathway for the spirit to rise along the same axis around which the heavens revolve. The pyramid thus became both tomb and compass, a fixed point in the cosmic order. The precision of this alignment is so astonishing that modern researchers once speculated about the use of magnetic compasses or other instruments that did not exist in ancient Egypt. But the truth is more elegant. Through careful observation and patient repetition, the Egyptians achieved astronomical accuracy that would not be surpassed until the invention of the telescope. The slow precession of Earth's axis has since shifted the positions of Kochab and Mizar, but when the pyramid was built, their alignment was perfect. Even more remarkable is that all three major pyramids at Giza share this same orientation. Their corners are synchronized not only to one another, but to the cardinal points, suggesting that a unified system of measurement guided their design. Each pyramid mirrors the other, like notes in a symphony played across stone and time. This coordination implies a central authority of architects and astronomers working together, verifying alignments through repeated observation and marking them across the plateau. The connection between the pyramids and the stars extends beyond their orientation. When viewed from above, the three pyramids of Khufu, Khafre, and Menkaure align roughly with the three stars of Orion's belt Al-Nitak, Al-Nilam, and Mintaka. This resemblance is not exact in scale but striking in pattern. To the Egyptians, Orion was the celestial manifestation of Osiris, the god of death and resurrection. Aligning the pyramids with Orion may have symbolized the pharaoh's rebirth, his soul joining the divine pattern in the heavens. The Nile, flowing nearby, mirrored the Milky Way, the celestial river along which the gods were said to travel. In this vision, Giza was not a city of the dead, but a reflection of the cosmos itself, a terrestrial sky. Astronomers have debated whether this correlation was intentional or coincidental. Statistical analysis suggests that the placement of the pyramids relative to Orion's belt could not have been random. The differences in size between the three pyramids even correspond roughly to the brightness of the three stars. Khufu's being the largest and brightest, Menkaure's the smallest and dimmest. Whether by design or divine symbolism, the effect is undeniable. The builders transformed the heavens into geometry, immortalizing the sky in stone. Modern measurements confirm that the pyramid's corners are aligned to within a fraction of a degree to the cardinal directions, and the east and west sides are nearly perfectly parallel to the rising and setting sun at the equinoxes. This harmony between solar and stellar geometry reflects a dual understanding of time, the daily journey of the sun, and the eternal rotation of the stars. It is the balance between mortality and eternity, light and darkness, life and afterlife. Recent high-precision surveys using satellite mapping have revealed that the pyramid's alignment may have been achieved by using the shadow of the sun as well. During specific days of the year, at sunrise or sunset, the shadows cast by vertical poles would align perfectly east-west. The Egyptians, ever meticulous observers of light and shadow, could have used this solar method to verify their stellar measurements. In doing so, they united the two great clocks of the sky, the sun that governed the day and the stars that governed the night. The pyramid's orientation was not a static feature. It was the foundation of its symbolic purpose. Each side represented one of the four corners of the cosmos, and the apex pointed toward the undying stars. The design mirrored the Egyptian concept of the world, a flat plane beneath a domed sky, ordered by divine balance. The pyramid was not only the pharaoh's tomb, but also the axis of the world, a bridge between creation and eternity. As the centuries passed, the casing stones that once shone in the sunlight were stripped away, and the precise lines of the pyramid became jagged. Yet, its orientation remains perfect. No erosion, no earthquake, no passage of time has disturbed its cosmic symmetry. Even now, when viewed from the air, the Great Pyramid's sides still trace the cardinal directions with astonishing fidelity. It stands as the oldest and most accurate observatory ever constructed, one that does not observe the stars, but embodies them. The builders who watched the sky and set their stakes in the sand understood something fundamental about existence, that permanence comes not from defying nature, but from aligning with it. By anchoring their monument to the movement of the heavens, they created a structure that transcended both time and belief. The Great Pyramid is not merely aligned with the stars, it is part of them, a mirror of the cosmos carved into the face of the earth. As the light of the stars shone upon their finished work, the builders might have believed that their task was complete. But beneath their feet, under the very bedrock of Giza, another mystery waited, a world hidden below the surface, where stone gives way to darkness and where the secrets of water, ritual, and the afterlife intertwine. Beneath the pyramids, hidden from the blinding light of the desert sun, lies a world carved in silence. This is the realm beneath Giza, a network of chambers, shafts, and tunnels that stretch under the plateau like the veins of a living organism. It is here, deep in the limestone bedrock, that the first foundations of eternity were laid. Before the pyramids rose into the sky, the builders looked downward into the heart of the earth, and from that stone womb, they shaped their monuments to the gods. The descent begins at the base of the Great Pyramid itself, through the narrow tunnel known as the Descending Passage. Sloping downward at a precise angle, it cuts through layers of solid limestone, its walls smooth and deliberate. This tunnel leads to a chamber far below ground level, rough-hewn and unfinished, where ancient dust still lies undisturbed. Archaeologists call it the Subterranean chamber, and it is one of the most enigmatic rooms in Egypt. Carved directly into the natural bedrock, it bears no decoration, no inscriptions, no evidence of burial. Its ceiling is uneven, its floor pierced by a mysterious pit that descends even deeper into darkness. Why would the builders of the most precise structure in the ancient world leave this chamber incomplete? Some scholars believe it was an early design abandoned when plans changed, a relic of trial and error. Others suggest it served a symbolic role, a representation of the underworld, the primordial abyss from which creation began. In Egyptian cosmology, the act of creation emerged from the watery chaos known as Nun. The subterranean chamber, hidden beneath millions of tons of stone, may have embodied that myth, the pharaoh's link to the origins of existence. Surrounding the Great Pyramid are other mysteries carved into the rock. Excavations across the Giza Plateau have revealed an intricate system of tunnels, shafts, and chambers extending far beyond the boundaries of any single monument. Some of these passages connect tombs, others seem to lead nowhere, disappearing into darkness. The purpose of these subterranean structures remains uncertain, but they speak of an engineering vision that extended both above and below the surface. At the base of the causeway, leading to the Pyramid of Khafre, lies one of the most enigmatic sites ever discovered, the Osiris Shaft. Hidden beneath a series of vertical shafts descending through limestone, it was first explored in the late 20th century, after being flooded for centuries. Divers descended through 3 levels of stone-cut chambers, each connected by vertical shafts and filled with water drawn from the ancient water table. At the lowest level lies a central island of rock surrounded by a deep pool, accessible only by narrow tunnels. On this island rest several granite sarcophagi, perfectly carved and aligned, but empty. The Osiris Shaft's architecture is unlike any other known tomb. Its multi-level design, water-filled chambers, and symbolic alignment suggest it served not merely as a burial site, but as a ritual complex. The island in the center evokes the myth of Osiris, the god of resurrection, who was said to have been entombed in the earth and reborn from its depths. The flooding may not have been accidental. Water was sacred, representing the boundary between life and death, chaos and order. The shaft thus becomes a symbolic gateway, uniting earth, water, and eternity. Ground-penetrating radar and electrical resistivity surveys conducted across Giza have confirmed the existence of additional voids and passageways beneath the plateau. Some follow the natural fractures in the limestone, while others appear to be deliberately cut. One of the most intriguing discoveries lies near the Sphinx, a network of tunnels and cavities that suggest a connection between the Sphinx Temple, the Valley Temple, and the plateau's inner layers. Though these passages remain largely unexplored, they reinforce the idea that the builders conceived Giza as a unified complex, an interlinked system of sacred and functional spaces extending above and below ground. The geology of the plateau itself played a crucial role in this vision. Giza's limestone bedrock is not uniform but layered, alternating between hard and soft strata. The ancient engineers exploited this structure, carving into the softer layers for chambers and leaving the harder ones intact to bear the weight above. This natural foundation allowed them to create underground spaces without compromising the stability of the pyramids above. Every shaft and tunnel was planned with an understanding of the Earth's composition, a harmony between architecture and geology that speaks to extraordinary foresight. Water, too, shaped this hidden world. Beneath the plateau runs the ancient water table of the Nile, which in the Old Kingdom lay higher than it does today. Some of the lowest tunnels were carved directly into these wet layers, where groundwater seeped through porous limestone. Far from avoiding this challenge, the builders incorporated it. The reflective surfaces of the water may have been used in rituals invoking rebirth, or perhaps to cool the air within the subterranean spaces. The concept of water as the source of creation appears repeatedly in Egyptian myth, and here it takes physical form, the eternal beneath the eternal. Archaeologists have long debated whether these underground structures served purely religious functions or practical engineering purposes as well. Drainage systems have been identified beneath some pyramids, suggesting that channels were built to redirect groundwater and prevent flooding. These could have doubled as symbolic pathways, blending utility and belief in a single design. In ancient Egypt, the practical and the spiritual were never separate. Both were manifestations of divine order. The builders also understood the need for stability. By cutting deep into the bedrock, they anchored their monuments to the living earth. The subterranean chamber beneath the Great Pyramid is not merely a void, it is a socket into which the pyramid itself is fitted, binding the structure to the planet. In modern engineering terms, it is a foundation lock, distributing the immense weight of the pyramid evenly across the limestone platform. The Egyptians may not have known the term load distribution, but they mastered its reality through observation and precision. Explorations using advanced scanning techniques continue to reveal new anomalies beneath Giza. In recent years, microgravimetric surveys have detected subtle density changes under the plateau that suggest even more cavities awaiting discovery. Whether these are unfinished tunnels, ritual chambers, or natural voids adapted by human hands remains unknown. Each new finding expands our understanding of how deeply the builders shaped their environment, literally embedding their civilization within the earth. When seen as a whole, the subterranean network beneath Giza is not a collection of disconnected tunnels, but an architectural philosophy made manifest. The Egyptians saw the world as a layered cosmos, the sky above, the earth in the middle, and the duat, the realm of the dead, beneath. The pyramids were built to unite all three, and the subterranean chambers formed the gateway between them. Every descent mirrored the pharaoh's journey through darkness toward rebirth. Standing above these hidden depths today, tourists see only the sunlight and the sand, but under their feet lies a labyrinth designed with intention. The foundations of eternity were not laid merely in stone, but in understanding the merging of geology, hydrology, and theology into a single, seamless vision. From the depths of the bedrock to the peak of the pyramid, the builders of Giza created a complete universe, bound by precision and purpose. Their tunnels and shafts were not secret by accident, but by design, intended to outlast all who would later seek to understand them. Beneath the sands, they anchored not just monuments, but meaning itself. Before the first block was ever moved, before the ramps were raised or the quarries opened, there was a plan, a design so methodical and exact that it guided every hammer strike for decades. The Great Pyramid was not built through improvisation. It was born from measurement, mathematics, and the understanding that precision itself was sacred. Beneath its grandeur lies a blueprint of intellect, drawn not on papyrus but into the minds of its builders. On the Giza Plateau, archaeologists have uncovered the remains of a complex network of workshops, barracks, bakeries, and administrative centers. Together they form what is often called the Pyramid Builders' Village. Here, thousands of craftsmen, engineers, and laborers lived in an organized system unlike any other in the ancient world. The discovery of this settlement shattered the myth of slave labor. The builders were not chained, they were citizens, trained specialists working in shifts under state supervision. Every block, every alignment, every measurement followed a unified standard. The Egyptians used a measuring rod known as the cubit, approximately 52 centimeters long, divided into palms and fingers. With this simple instrument and ropes stretched tight between posts, they established grids that mapped the pyramid's base with geometric clarity. Wooden corner posts marked key points, and ropes were drawn diagonally across to verify right angles. Such triangulation produced foundations with errors measured in centimeters across hectares of stone. Modern surveyors using laser equipment have confirmed that the base of the Great Pyramid is level within less than 2 centimeters, an achievement unequaled for over 4,000 years. The Egyptians' mastery of geometry went beyond lines and angles. They used ratios to define the pyramid's slope through a concept called the seekt, the horizontal displacement per vertical rise. In Khufu's pyramid, this ratio was 21 palms per 28 fingers of rise, corresponding to an angle of about 51 degrees. This consistency was maintained across every course of stone, proving that the builders worked from a centralized plan rather than adjusting as they built. The seekt was not just mathematical, it was symbolic. It reflected harmony between heaven and earth, where vertical ascent met horizontal order, a balance mirrored in their theology of Ma'at. Inside the builder's village, archaeologists found evidence of meticulous record-keeping, fragments of ostraca and limestone flakes with notes, delivery counts, and instructions. These were the spreadsheets of their age. Supervisors coordinated crews of workers, each assigned to specific sectors of the pyramid. Teams were organized into divisions of about 2,000 men, further subdivided into smaller units of 100. Each unit had its name, its foreman, and its tasks. Inscriptions left inside the pyramid graffiti from the workers themselves bear team names like the strong right arm of Khufu. Such organization ensured not only speed but quality control. Tools were simple yet precise. Copper chisels, wooden mallets, plumb lines, and leveling cords formed the foundation of their engineering toolkit. Experiments with replicated tools have shown that when copper is hardened by hammering, it can cut limestone efficiently before dulling. The Egyptians understood this and rotated tools frequently, maintaining sharpness through constant reworking. They did not rely on miracle metals or lost technologies, only on discipline and understanding of materials. Even the transport of materials was scheduled with precision. The Mirror papyri discovered at Wadi al-Jarf reveal a bureaucratic system that tracked daily deliveries of limestone to Giza. Each entry notes the number of trips, the cargo, and the supervisors responsible. This level of documentation rivals that of modern construction logs. It shows that the pyramid project was not a spontaneous act of devotion but a national enterprise coordinated across hundreds of kilometers. The placement of the foundation stones followed a ritual of measurement and verification. Surveyors known as the rope stretchers were elite specialists, respected for their skill in land measurement and astronomy. They worked with geometric instruments, aligning the foundation grid to the stars and horizon. Once the baselines were fixed, masons cut channels into the bedrock and filled them with water to ensure perfect levelness. When the surface was drained, the remaining traces of moisture revealed the high and low points, allowing precise leveling across vast distances. Above this foundation, planning continued with relentless consistency. The internal passages, chambers, and shafts were positioned according to mathematical sequences that linked height, length, and angle into an integrated design. The Grand Gallery's slope, for instance, mirrors the overall angle of the pyramid's exterior, forming a geometric echo between the inner and outer structure. Nothing was accidental. The pyramid's geometry is recursive, each part reflects the whole, a hallmark of deliberate design. Beyond mathematics, the organization of human labor was itself a form of engineering. The workforce was sustained by a supply chain of astonishing efficiency. Excavations revealed vast bakeries capable of producing thousands of loaves of bread daily, and breweries that supplied beer as a nutritional staple. Storage magazines held dried fish, fruits, and grains brought from across Egypt. Medical instruments found at the site indicate that the builders had access to care and treatment, suggesting an early form of occupational medicine. A healthy workforce was an effective one, and the pyramid's progress depended as much on human welfare as on design. This social coordination reveals something profound about Egyptian civilization. The pyramid was not just the vision of a king, it was the collective expression of a people who believed their labor could touch eternity. The project united religion, mathematics, astronomy, and logistics into a single purpose. It was both national infrastructure and divine offering. The state mobilized resources on a scale unmatched until the modern era, yet without chaos. Order was maintained through measurement, rhythm, and shared belief in the purpose of the work. Planning also extended into materials science. The builders experimented with different quarrying and transport methods, optimizing for distance and durability. Chemical analyses of the limestone show varying compositions between core and casing stones, suggesting deliberate selection for function, denser stones for strength, finer stones for polish. Some scholars propose that certain limestone blocks may have been partially reconstituted from powdered stone and binding agents, forming early examples of geopolymer technology. While this theory remains debated, it underscores the Egyptians' willingness to innovate. They were not confined to tradition, they were empirical thinkers testing the limits of their craft. Mathematics guided their every decision. The pyramid's height-to-base ratio produces a shape that encodes the value of pi within less than 1% error. Whether intentional or incidental, it demonstrates an understanding of proportion and curvature beyond mere practicality. The slope creates a structure that naturally resists collapse under its own weight, an optimization of form and function. This blend of symbolic and structural harmony defines Egyptian architecture, the pursuit of balance between what is seen and what is eternal. As the pyramid neared completion, inspections became more frequent. Each finished course was checked for levelness and alignment before the next began. The architects used sighting rods and leveling boards, communicating measurements across long distances through mirrored plumb lines. Every deviation was corrected immediately, ensuring that small errors never accumulated. Such obsessive precision is what allowed the pyramid to stand for 45 centuries without measurable distortion. The greatest achievement of the pyramid builders was not the stone itself, but the system behind it. The merging of planning, labor, and faith into a single, enduring process. They transformed work into ritual and engineering into philosophy. In their world, measurement was divine language. To measure was to honor the gods by bringing order to chaos. The story of the Great Pyramid is, in truth, the story of humanity discovering that precision could outlast time. Each rope stretched taut, each cubit checked, each stone aligned, was an act of faith in reason. From the quarries to the stars, their calculations echoed the belief that the world itself was measurable, comprehensible, and eternal. And through that belief, they created the most enduring testament to human intellect ever carved from Earth. For centuries, the Great Pyramid stood as an unchanging monument, massive, immovable, and silent. Yet in the last few decades, it has begun to speak again, not through ancient voices, but through the instruments of modern science. With every new scan, every beam of radar and burst of cosmic radiation, the pyramid reveals that it is far more than a pile of stone. It is a structure of precision so complex that even now, 45 centuries later, we are still learning how much the builders knew. The first tools of rediscovery were those of exploration. In the 19th century, surveyors measured the pyramid with ropes and telescopes, marveling at its accuracy. But it was not until the 20th century that science began to truly probe beneath its surface. Ground-penetrating radar, infrared thermography, and microgravimetric scans opened windows into the pyramid's interior, showing patterns that no human eye had seen since the time of Khufu. These technologies revealed hidden voids, temperature anomalies, and subtle density shifts, clues that the structure still held secrets within its massive body of stone. In the early 21st century, the Scan Pyramids project transformed the study of ancient architecture. Using muon tomography, a technique originally developed for particle physics, scientists measured the paths of cosmic particles as they passed through the pyramid. Because muons interact differently with solid stone and empty space, they allowed researchers to visualize the pyramid's interior in 3 dimensions. What they found shocked even the most skeptical Egyptologists. Above the Grand Gallery, deep within the core of the pyramid, a vast empty space was detected, an unknown void stretching more than 30 meters in length. It was the largest internal discovery since the 19th century. The void, dubbed the Big Void, lies parallel to the Grand Gallery, suggesting a deliberate connection rather than a random anomaly. Its size and position imply that it may have played a structural or symbolic role in the pyramid's design. Perhaps it served to relieve stress, like the chambers above the king's chamber. Or perhaps it was part of a ritual architecture now lost to time. What made this discovery even more remarkable was its precision. The muon scans, repeated from multiple angles, confirmed that the void's geometry followed the pyramid's internal symmetry. Nothing inside the Great Pyramid appears random. Every empty space, every shift in density, aligns with an underlying order that suggests purpose and calculation. Thermal imaging has also uncovered new mysteries. When researchers scanned the pyramid's eastern face, they detected temperature variations in specific blocks, differences of several degrees between adjacent stones. These anomalies may indicate hidden cavities or variations in the internal structure. They might even point to secondary passages sealed long ago. Each new anomaly forces scientists to reconsider what they thought they understood. The pyramid is not a finished story, it is an evolving experiment still being read by those who listen. Material science has revealed another layer of complexity. The limestone blocks that make up the pyramid are not uniform. Their chemical composition varies subtly from layer to layer, suggesting that the builders deliberately selected or treated stones for specific functions. The casing stones, once gleaming white, contain a higher proportion of calcite, giving them greater reflectivity. The core stones are denser, designed to bear weight. Microscopic analysis shows tool marks consistent with copper chisels, but also hints of polishing with fine abrasives. These details prove that the Egyptians understood not only geometry, but material behavior at an astonishing level of refinement. A modern debate has emerged around the possibility that some of the limestone blocks may have been reconstituted rather than quarried. This idea, first proposed by the chemist Joseph Davidovits, suggests that certain stones were cast using a mixture of powdered limestone, water, and binding agents such as natron or clay. Tests on a small number of samples have revealed microstructures, unlike natural limestone, with air bubbles and mineral phases that might indicate artificial formation. While most geologists remain skeptical, the debate underscores how advanced the Egyptians were in manipulating their materials. Whether cut or cast, the result is the same stone shaped to perfection. Laser scanning has allowed researchers to map the pyramid's surfaces with millimeter accuracy, revealing patterns invisible to the naked eye. The sides, once thought perfectly straight, have a subtle concavity, bowing inward by a few centimeters. This curvature, intentional or not, distributes weight more evenly across the faces and reduces structural stress. The pyramid's architects may have discovered this through observation, incorporating it as a design feature centuries before modern structural analysis existed. Even the joints between the stones hold lessons in precision. When the pyramid was complete, the gaps between casing stones were less than a millimeter wide. Modern engineers estimate that if such joints were scaled to the size of a skyscraper, they would be tighter than those used in most steel frameworks today. The smoothness of these joints prevented erosion and added structural cohesion, turning millions of individual blocks into a single unified mass. The more scientists examine the pyramid, the more it challenges assumptions about ancient knowledge. Computer modeling of the structure's stability shows that its geometry is near optimal for a stone monument. Its height-to-base ratio minimizes the risk of collapse, and the stepped internal structure prevents shear failure under load. The pyramid's form was not an accident, it was a solution. Its designers discovered the equilibrium point between mass and shape, between weight and gravity. What is perhaps most humbling is how the builders achieved such perfection without modern instruments. No metal rulers, no compasses, no laser levels. Only ropes, plumb lines, water, and observation. Yet with these tools they created a monument whose alignments remain more precise than most modern buildings. This suggests a level of empirical science grounded in centuries of accumulated observation. The pyramid is not a mystery of lost technology, it is a monument to the persistence of human learning. Beneath the stones, scientists continue to explore. Ground-penetrating radar reveals that the limestone bedrock is cut by narrow channels, possibly ancient drainage systems or symbolic pathways. Some lead toward the so-called boat pits, where full-sized wooden vessels were buried beside the pyramid. These boats, built from cedar imported from Lebanon, were disassembled and interred as part of the pharaoh's journey to the afterlife. Their preservation for thousands of years in sealed chambers testifies to the builders' understanding of isolation and environmental control. Satellite surveys have further revealed subtle depressions across the Giza Plateau, marking the outlines of structures buried under centuries of drifted sand. These may be remnants of earlier temples, workshops, or even the quarries from which the first foundation stones were cut. The more we map the plateau, the more it becomes clear that the pyramid was not a singular project. It was part of a living, breathing complex of science, religion, and engineering. Modern technology, though powerful, still only scratches the surface. Every scan reveals new questions. Every theory opens new uncertainties. But what emerges through all these discoveries is a growing respect for the intelligence behind the monument. The builders of Giza were not primitive laborers. They were master engineers guided by observation, experimentation, and purpose. The closer we look, the more the pyramid resembles a bridge linking the knowledge of the past to the curiosity of the present. It stands as both a challenge and an invitation to measure, to learn, and to seek order within the chaos of the unknown. And as modern science continues to uncover the secrets of its design, one truth becomes ever clearer. The Great Pyramid is not a relic, it is a lesson, a message written in stone that speaks across time. Every discovery reminds us that beneath its ancient surface, the pyramid is still alive, with knowledge waiting to be understood. The Great Pyramid of Giza does not simply stand upon the earth, it stands within it, fused to the bedrock of human history like a cornerstone of civilization itself. It is not merely a relic of a vanished world, but a mirror that reflects what humanity is capable of when vision, patience, and precision become one. More than 45 centuries have passed since its completion, yet it remains the most enduring structure ever built by human hands. While kingdoms rose and fell, while languages changed and stars drifted across the heavens, the pyramid endured unchanged, unmoved, unbroken. Its legacy begins in the mind. For all its physical grandeur, the true marvel of the Great Pyramid lies not in its mass, but in the invisible web of mathematics and intention that holds it together. The ancient Egyptians understood something fundamental, that harmony could be built. Every length, every slope, every chamber was not only an act of construction, but a philosophy expressed through stone. The pyramid embodies the balance between heaven and earth, matter and spirit, time and eternity. To modern engineers, its geometry remains an object of fascination. The pyramid's base spans more than 230 meters on each side, yet its deviation from perfect square is measured in mere centimeters. Its sides face the cardinal directions with an accuracy finer than any compass could achieve until the modern era. Its height, now reduced by erosion, once equaled 1/2 of its perimeter divided by pi, a coincidence perhaps, but one so exact it borders on intention. Through proportion alone, the pyramid expresses the relationship between the circle and the square, between the finite and the infinite. The builders did not know our mathematical symbols, yet they understood the principles they represent. They worked not with abstractions, but with experience observation refined into law. They measured shadows, tracked the rising of stars, and learned that order was not imposed upon nature, but discovered within it. Their tools were simple: rope, wood, stone, and water. But through these tools, they achieved the precision of a modern machine. It was not technology that raised the Great Pyramid, it was understanding. The pyramid's design has survived every test that time could impose. Its shape, broad at the base, narrowing to a single point, gives it perfect stability. Earthquakes that shattered nearby temples left the pyramid untouched. Sandstorms scoured its casing, but its core remains immovable. It was built not to defy the desert, but to exist within it. The ancient engineers read the land as carefully as they read the stars. They chose the Giza Plateau not for its beauty, but for its geology, a limestone foundation strong enough to bear the weight of eternity. Beneath the stones lies an intricate network of carved channels and drainage systems that have preserved its base from flooding. Every natural challenge had an answer, and every answer became part of its perfection. Yet the legacy of the pyramid extends far beyond the boundaries of Egypt. Its influence echoes through the architecture of the world. The ziggurats of Mesopotamia, the temples of Greece, the domes of Rome, and even the glass pyramids of modern Paris all draw, consciously or not, from its geometry and symbolism. The pyramid's proportions taught later civilizations that beauty arises from balance and that strength is born of harmony. In its simplicity lies a universal law. Even in the modern age, the pyramid continues to shape scientific thought. Mathematicians have used its dimensions to explore ancient ratios and constants. Physicists have studied its form as a natural structure of equilibrium. Its alignment with the cardinal points has influenced astronomical observatories from the Middle Ages to the present. In architecture, its load distribution remains the model for stable design. And in the language of symbolism, it still stands for aspiration, the upward motion of human will. But perhaps its greatest gift is the lesson it offers about collaboration. The pyramid was not the work of a single genius or a divine intervention. It was the product of thousands working as one. Farmers, masons, surveyors, and mathematicians, united by belief and purpose, gave their lives to a vision larger than themselves. Their society, valued knowledge and coordination as much as strength. Their tools were shaped not just by necessity, but by curiosity. This unity of intellect and labor is what built the impossible. Modern excavations at Giza have revealed this human story written in clay shards and workers' graffiti. Teams bore names like the Drunkards of Menkaura and the Friends of Khufu. These were not slaves but skilled artisans, proud of their work. Their marks, scrawled in red paint on the hidden walls of the pyramid, are signatures of humanity, proof that behind the precision lies personality. They were not building a mystery, they were building a legacy. The pyramid's endurance is more than structural, it is philosophical. In an age when civilizations measured time in centuries, the Egyptians thought in millennia. To them, permanence was not arrogance but reverence. They believed that the physical world could embody the eternal if built in harmony with the cosmic order. The pyramid's alignment with the stars, its foundation in the earth, and its towering symmetry are all expressions of that belief. In their architecture, they encoded their theology that the soul ascends through knowledge and that knowledge itself is divine. Even now, the pyramid speaks to us through silence. It teaches that greatness requires patience, that understanding requires humility, and that permanence is achieved through harmony, not conquest. It reminds us that civilization is not measured by what it destroys, but by what it preserves. Every civilization after Egypt has sought permanence in its own way, but few have matched its clarity of purpose. The Great Pyramid endures not because it was built to last, but because it was built with understanding of how nature lasts. Scientists studying the pyramid today continue to uncover layers of ingenuity that defy expectation. Advanced modeling reveals that the internal chambers were placed in ways that evenly distribute stress throughout the structure. The internal geometry acts like a network of stone buttresses, an architectural foresight thought to have been invented thousands of years later. The builders achieved through intuition what modern engineering calculates through equations. This is not primitive construction, it is empirical science expressed in stone. Beyond the realm of science, the pyramid has become a mirror for human thought. Philosophers see in it the shape of aspiration, mathematicians, the logic of proportion, poets, the silence of eternity. It stands as proof that human reason, guided by faith in order, can create something beyond the lifespan of empires. Its form has inspired everything from religious temples to skyscrapers, each new age reinterpreting its meaning. Yet the essence remains unchanged, a monument to what happens when knowledge and purpose align. Even as satellites orbit the Earth and telescopes gaze beyond our galaxy, the Great Pyramid continues to point us toward the same truth. We are part of a continuum of builders each generation, adding its own layer of understanding to the foundations laid before. The Egyptians carved their knowledge into stone, we carve ours into data and light. But the impulse is the same, to reach upward, to make sense of the stars, to turn time itself into structure. If the pyramid teaches anything, it is that no mystery is diminished by understanding. The more we learn about it, the more it humbles us. Each discovery reveals not magic, but mastery, proof that human ingenuity is the most powerful force on Earth. And so, beneath every block of the Great Pyramid lies not mystery, but mastery. Beneath its surface lies a civilization that measured not only stone, but the very rhythm of existence. They built monuments that would outlast the world that made them, and in doing so, they wrote the oldest message still legible to humankind. We are here, we understood, we built for eternity.